Okay, so I work for NIST. This is the National Institute of Standards and Technology. It's metrology institute for the U.S. and a standards institute for the U.S. I work in the computer security division, so I'm a cryptographer. I can't tell whether cats are dead or alive, and I'm puzzled by the questions. So I know no quantum stuff, okay? But yeah, and there's a mystery of why I was invited to talk here. So presumably you'll figure it out and tell me. Okay, so I'll show you what this thing is. Okay, it's something. It's a. Oh, that should have clicked that. There you go. So I can't go through all this in detail, but there's a web page that we've set up there where let me do this. Yeah, there's a summary there. It says, we're implementing a prototype. That's I'm trying to get rid of that. I would like this to be a service to the internet community. But the lawyers are very, very nervous about that, so they make me call it a prototype. It's been running now for over a year without interruptions. Before that, we had a few interruptions. And it basically puts a random number on the web every minute. Okay? And there, let me first show you the actual interface that you would access if you were going to use these things. This is you could, yes. So a good friend told me I would go down in history as the idiot who made it possible for all kinds of people to use public randomness to create their private keys. And the lawyers also smelled something funny and made me put this in red and big, okay? Do not use it to generate secret keys. These are public, okay? And here they are. So you can, there's, unfortunately, there's something called seed value, which is the raw output of two random number generators. We just bought these things and hooked them up. And at this point, we XOR. Probably going to change that. We XOR the two so that if anyone fails, this thing is still OK. They're classical generators. They just gather noise from environment, and it's not a quantum generator. There's a previous output. These outputs are chained over time. So we have a year's worth of outputs every minute. They're chained by a hash chain. And the way this is done is you take the last output, the current output of the current output of the generators, the last output of the beacon. You sign everything along with the timestamp information and other sort of metadata. You sign it with a secure hash function, and then and then you hash the whole thing, and that's the next output value. Okay, so previous output, next output. So this guy is going to be in this place at 154, and this is going to be regenerated. Why would we want to do this? Because this is intended to serve as a historical record of random numbers over time. So if two people had some sort of agreement saying, we're going to use a random number next minute or at 12 p.m. today to decide something, then if it's 6 months later they want to somebody wants to claim that the other person robbed or cheated or didn't go according to protocol, you can always interrogate the database, and you can't come to NIST and say, I'll give you $1 million to change that one entry. Okay? If we could, so we're preventing ourselves from being able to do that. We can't change an entry without making a whole invalidating, 6 months worth of other data. Okay. Okay, so that's the output, and there's the REST interface to use that. Now, why would you want to use this? So my position, let me see. Okay, well, why don't I just, yeah, I can't, we have no time. You know how to do this? Yeah. He was my professor. So he can look at that. These physicists, computer scientists, they're so smart. Okay, so it's very hard to explain to people why you would want something like this. So I came out with some possible applications, and I wrote them there. But officially, my position is that it is for academia and for industry to find out applications for this and publish them and do some and debate and start writing applications. But I put some as examples. So unpredictable sampling. So this, so I worked at a chip factory for summer once, and it's pretty interesting what happens inside there. The people remember the operators like spat on the wafers and then called they cooked the thing, and then they called the engineers and say that there's something wrong with this batch, right? And then they would sit back while the engineers debated about whether the radon gas was the wrong level and all that. Also, we knew that at sometimes when the air got a little too dirty, we were going to have a lower quality wafer output, and maybe the air got a little dirty when it got too hot and something wasn't working right. There's all kinds of environmental stuff that affect the output of an industrial process like this. At the same time, we have quality controls. There's in the manufacturing room, there's these engineers who basically look good when lots of the chips look good, right? So you go and you test these things at random, and of course the guys inside, they know that they don't want to check at 4 p.m. when that operator came in, and every time she comes in, something goes bad. I said, okay, let's take away from the person on the floor there the claim of having picked at random, right? So what they would do is say, you pick the chips that, some deterministic algorithm, you apply that, and that gives you a bunch of serial numbers of what chips you're going to test, and those you are going to test, okay? You're not going to, so it helps in that kind of scenario. There's many more people when you do assays for health stuff, when you're doing drug tests, all kinds of things that really depend on randomized trials. Right now, we often have to take on faith that these things were actually random. This is taking away, this is helping gain some assurance in that. Okay, so that was one. And I have until 2:15. Is that right? 2:20 because I was late. Okay. And questions. So we're going to go fast. New secure authentication mechanisms. Okay, so I'm not going to click that link. Again, you could click it, and you'd see that in some cryptographic scenarios, it is so for example, to know that, suppose that in order to get through that door, I need to prove to the door that I know the factorization of some RSA number. RSA is the standard public key crypto system. And one way to show them that I know a prime factor of this composite module is to just give it to the door, but then we don't trust these things that they can actually get the secret and then lose it to the next person who uses it, or be connected surreptitiously to some other circuit. So normally the paradigm, in the modern paradigm for that kind of thing, is to convince the door that I know something without actually giving it the secret. Okay. An easy way to convince somebody that I know the factorization of a number n is to show that I can compute the square root, modular square root of a random number. Okay, so I could just I could just go to the door and say, here's a random number and here's the square root. Unfortunately, that doesn't work because I can just do that very easily. I grab a number, I square it, and then I claim that the original number that I grabbed was, no, I claim that the square that I have is a random number that I proceeded the other way around. I went from the squared to the square root, which can't be done unless you know the factorization. So the other alternative is for the door to give me the number. But it's been an open problem for many, many years whether the door could actually learn how to, no, this is actually easy. No, for that one, this is easy. The door can steal the factorization from me by doing that. They will cheat. They will not give me a random number. They will do the same. They will grab a number, square it, give it to me, and I have a chance of 1.5 of telling the door my factorization. Okay, that's just one simple scenario of a very wide field of zero knowledge proofs. These are proofs that you make where you control what you're proving to a very minute detail. So that can be fixed, but it's complicated. So here you can just say, grab a random number from the beacon, give him a square root, and you go through. Okay? So, and there's probably much such things. Secure multi-party computation. This is something you have two people that want to compute the function of their private inputs. You may have heard this in the Yale's millionaire problem. Two millionaires. I guess millionaires don't want to tell each other how much they're worth, but they really want to know whether they're richer than the other guy. Okay, so how do they solve this problem? They come and talk and
When Yahoo invented that, it was a distinction to be a millionaire, not anymore. The two billionaire problem.
Yeah, that's right. Yeah, okay, yeah. Yeah, these are billionaires. Yeah, so that's an example of a case where we jointly want to compute something, and we don't want to tell each other secrets in the process. Okay, so the protocols for that involve a lot of random numbers, and they become very easy if you can assume that these numbers are not controlled by any of the two parties. And in a two-party scenario, that costs something. Can be done, but it's costly. So again, if you can access randomness from the environment, it would be very nice. And this is something that maybe maybe you can find some of it that use for the techniques that you guys are exploring in this workshop, right? Okay, can you trust it? Well, we live in interesting times. If you read the blogs about the NIST beacon, I'm called all kinds of names. I'm supposed to work for the NSA, and there's a lot of mistrust of anything that the government does, and rightly so, I should say. I mean, this is being YouTube, right? Okay, so there have been suspicious activity that maybe or maybe not denotes some sort of problem. Okay, I'm talking legalese, right? Yeah. So there's been lots of bad stuff happening in the so understandably, the community can't trust the government-produced string with an assertion, unverifiable assertion like this is random, right? So that's again where what you guys are debating here is important. You're producing ways to guarantee randomness. And so are we at NIST too. Elliptic curves, okay, so yeah, so elliptic curves are an important primitive in cryptography. These are right now fixed curves produced by NIST, well, produced by the NSA, blessed by NIST, and because of all this other bad stuff that's been happening in the last year or so, there's a lot of distrust of these curves. This actually is a very interesting thing because there's no way that you can really defend that mistrust from a technical point of view. There's, in the previous, the thing is that there's another elliptic curve thing, which is something that NIST has apologized for and retracted it, and it's shown up in Snowden documents. It's a disaster, okay? That has spilled over to this area where it's a very different scenario, but the people out there, if you're not specialists, you just don't trust it. So there's reasons to change these now. To change them, both because of the credibility problem and because we know now a lot more about picking these things. And we know better criteria now to pick these things, of how to pick these things. And one scenario is that we're going to talk the community, the academia, industry, standards organizations, they get together, talk, and decide on a framework, on a set of criteria that will land them in a class of curves, a large class of curves. And then, of course, everybody wants to say, I'm going to pick them from there, right? And they say, and I'm going to claim to have picked them at random. So one of the possible scenarios for which I'm actually going to start some sort of proof of concept about this is that we want a community to be able to pick at random a large string. And we need that to be so that the whole world can be observing, and the protocol has to be such that nobody, that as long as you believe one of the parties had security and privacy, security and secrecy, then the resulting string is truly random, not known before by anybody, not controlled by any security agency, and so on. Minutes? 2 minutes? 5. Okay. Okay, so one of the things I've been doing is well, there's a problem here, is that the one thing we can't prove is that we didn't know this string ahead of time, that we didn't spend the last year pre-calculating so that we knew that at this time we had a bunch of strings and we could pick one that hurt some particular application. So for applications that would actually need for which we could hurt you if we actually cheated, by cheating means we knew this string ahead of time and let the bad guys know. Such an application is voting. Okay, so this has been proposed for electronic voting to go and decide which machines you're going to audit. So electronic voting is becoming more and more prevalent in the countries, and people are concerned that these machines are somehow sabotaged. You really want to have a post-election audit, but who picks which machines to audit, right? So if NIST is in cahoots with somebody who wants to steal the elections and sabotage the machines, we could give them, way ahead of time the number and tell them that which machines are going to be audited and they can cheat that way. Okay, I'm just going to leave this here. It's been a kind of a crusade of mine for almost 20 years now, thinking that the internet environment might, should, or will have a number of services that that are sort of communal. Timestamping bulletin boards, notary publics, PayPal type, append-only bulletin boards, anonymizing nodes, attribute providers, identity providers. There's a huge, one of my main jobs at NIST is to worry about the privacy of citizens in the US. The identification problem is something that there are many important developments and a lot of problems in assuring that privacy and security of users is maintained. Okay, and I claim that there are services that we haven't thought about yet that should show up. This requires a different model, different trust model than we've inherited from cryptologists and computer security people. I just wrote this morning online. We're much more than a sum of nodes. We're a group of people and institutions with nuanced trust relationships and varied incentives. See, from crypto, we really inherited what we call the Leviao model. There's two parties. They distrust each other fully. They have these secrets. There's no much nuance in the kinds of trust that they have about each other, and they have possibly an eavesdropper that's also bent and doing all kinds of bad stuff. Okay, I'll end here because I've run out of time, but since the slides are going to stay, I left a bunch of stuff in the slides that you might want to look at if you so want. Thank you.
Thank you, Rene. I've never seen a talk end at 6 out of 12.
Yeah, innovating in all kinds of ways. Yeah.
It's really novel, yes. Questions?
Yeah.
On your previous slide, when you listed possible applications, you had a PayPal type service. Are there any proposals for some system in place, like Bitcoin, on a moderated level like this, or the government? For that?
No, I mean, I'd be quite upset if I was the government, just from an economics point of view. You'd lose control of the money supply. So I don't think that Bitcoin would be promoted by the government, but the population is promoting it, and there's a lot of crypto work. And I get mail from time to time about the use of the beacon for that. Bitcoin, basically you create money by running cycles. You're using computer cycles, and there's this imbalance that there's people that have a lot of computers for a lot of time, and people that don't have much, and they're saying, we really want some assurance that this process started no later than an hour ago. And the beacon is one way to do it, because your starting point will be the number created at an hour ago, which wasn't known before. And there's another scenario where we could cheat, in this case with money. We could tell somebody, a year ahead, and you're going to be rich,
So if I understood, even if we pay you $1 million, you still cannot produce a number that we tell you what to produce, because it goes through this hash function.
Yeah, that's,
On the
yes,
other hand,
yeah.
what you can do, if we pay you enough money, is tell us what will come out in a year.
Yes. And
But
if
we
you
can't order it.
Right, exactly. You can order, though, the last 20 bits of the number, though, because we can. So a low entropy application is another area.
That's unless we paid you enough money to choose a weak hash function.
Right, yeah. No,
So
NIST doesn't choose them anymore. So,
how much do you cost? What's your price?
No price.
Everybody's being YouTube.
Other questions?
Peace on love on earth. I'll go for that.
Oh,
Yeah. Give me that, and I'll
that's a good
try
price.
to.
Another question. So NIST
has those standards for random number generators, right?
Yes.
So I wonder, I'm sure you have applied your standards to the output of the beacon, and maybe not.
Okay, so there's a standards for random number generators that apply to how you use this thing. That includes the sanity checks, on-time sanity checks, and probably some stuff about reseeding. But I think you may be talking about the statistical test suite.
Right.
Okay, so the statistical test suite, it's probably our fault. It is understood out there as a way to sort of say the number this generator is good. That's really not possible. You can never say generator. You can just say it's not horrible. So these things are really meant as a sanity check to catch something that's malfunctioning. If you think about how do you test actual strings and say this is. In fact, what they do, if they pass those tests, that you lower the entropy, because the only way you can make those tests is by throwing away things that look, throwing away a set of strings, right? Yeah. So, yeah. So, yeah. Yeah.
Two questions?
Yeah.
If I understood, you use two independent sources and then just XOR them together, instead of using a Santavezzer-any type of way to combine them in a more secure way. And I was wondering why.
What way, sorry?
Santavezzer-any?
Santavezzer. Okay, so we,
Because
yeah.
XORing it is not the most secure thing to do. Unless you really trust them to be
Yeah,
independent.
so that has an interesting answer. Do you want to time?
Well,
Yeah.
fine.
So the alternative is to basically concatenate and hash, or use some either. So you compose the game as the following. One of the generators learns the other output before it actually generates and gets to cheat. In that scenario, XORing is terrible because the bad generator has the full control of what the output is. Whereas if you do this other stuff, you don't. Okay. From my perspective, having to deal with the NIST lawyers, my nightmare scenario is that one of these things fails and I don't notice or we don't notice for a month, and one of these generators has been outputting 0, 0, 0, 0, 0, 0, and then we've somehow this is transparent to the process that hash, concatenate, and hash, and then NIST will look bad, and that's more important at this point. What's more important to me at the point where I need to keep this project alive? We are actually switching to the other model.
Okay.
Yeah.
I have another question, but will the next speaker come and set up while he's
Yeah.
finishes? Please.
But
So
yeah.
my other question, which is maybe more relevant to this group, is why are you not using at least one of the two generators based on quantum stuff?
Yes. So I ran out of time. I'm sorry. So 5 minutes of this was actually going to the description of the where we're spending most of the money in this project, which is in actually doing a loop-free bell test generator. There's millions of dollars in this project, and the physicists get it all, right? And they're flipping photons left and right. And there's one of them here, I think, and maybe. Yeah. So maybe locate the physicists and get an update on how that is going, because they're, I don't understand that, but this is really cool work. I mean, so they're doing these. You send basically what sells in the government? It sells the idea that some foreign power is not determining your random output. So the assurance that we seek is that if that foreign power is going to interfere with this, they have to get within a certain time-space area, which we actually control. And that that sells in the US. Yeah. Okay, sorry, I took more. Yeah.